All right. So today was second summary due. Thank you for doing the writing center. They send me notice. So I record who's been there and so forth. On our submission, it is right down here. So we had second summary topics, that's where you found the assignment, and then our submission is right here. So if you have not submitted it, take your electronic file, click on the View Complete, all right? And that opens up a submission page. All right, that opens up the submission page. So from that submission page, you just type in your name. You are technical. So I don't know if this is what yours looks like or not. I can upload stuff myself. And then what you do is choose from either this computer, if it's on your personal computer, if you saved it to Dropbox, or from Google Drive. Selects the files, you upload. Once you select the file, you hit the upload button, and it will review it for plagiarism and so forth. All right. So all of our, just kind of going back to the major assignment page. So it was under here, major assignments. Summary number 2, submission. Click on the View Complete, and it opens up our page. All right. Make sure that gets done. This ends at 2 p.m., although it was due before class. So get it done. Other assignments. Campus event. That's due. It's due on Monday. All right. We also had what I listed as a pre-class assignment. This is suicide prevention. You've got the quiz. All right, so watch a YouTube video. You can have the quiz out and ready. All right, it's a dot file, and then you can write your answers as you watch this video, and then same thing. All that you have to do is click on this suicide prevention link here, and that opens up the upload page. Go ahead and upload it. A couple of you have already uploaded it. Thank you. I've already graded them, those that were uploaded, so you can check it out. This is an easy assignment. Easy assignment for participation points. Make sure that gets done. All right, make sure that gets done. That is due before the start of class next week, Wednesday, which happens to be the last day of the semester, right? Last day of the 8 weeks. Just a reminder, ASU webpage, check out your campus calendar if you were curious. At important dates, you can see your list view or the month view. You will see that the last day of classes is that week. And we have pre-registration. We are September 30th. First 8-week final exam start. So last class day is October 2nd. That is next week, Friday. And October 5th starts second 8 weeks. So check those out. Pre-registration, they have it up. So October 26th, pre-registration for seniors. That is senior classification, so, and that's based on how many hours you have. You have juniors on October 28th, so 2 days later. Sophomores, some of you are coming in with a lot of dual credit or a lot of transfer credits. If you had more than 30, you shouldn't have been required to take this class, technically, but that's if you had transfer credits, so transfer from community college. If it was all dual credits, then they do recommend you to take this class. There is a possibility, though, with your credits that you could be technically a sophomore, right? And that means you start registration on October 30th, all right? And then for everyone else that doesn't have at least 30 credits, then it is November 3rd, right? It is November 3rd. Before you can register, you have to be advised. There is an advising hold, and your advisor will remove it after you talk to them. Don't email your advisor and say, hey, I didn't come in, I have to register it today. Can you remove the advising hold? They will say no. They will say no. You have to go talk to them, either in person or some of them are doing Collaborate or Google Meets or Zoom sessions. All right. Hopefully none of them are doing emails. That's kind of a poor way to advise. So get advised. And the advising is going to start sometime in October, beginning of October. You will see the emails. I actually think Dr. Wagner said that they start next week, I think is when advising starts. Any questions? All right, move this over. We are almost done with our class. No. Add that bigger. So, what do we have left? Our last major ingredient is water. And that's what we're going to talk about today. We're going to talk about the effect of water and how it relates to some styles that developed on Monday. And then we're going to wrap up with presentation. So we're going to start with just background information on water itself. That's going to be our entire talk today. Let's see, and I'm going to probably switch colors as we progress. All right. So water. What is water? It's two hydrogens bonded to an oxygen. And that's our structure. Two hydrogen atoms bonded to the oxygen atoms. And this is important because what ends up happening chemically is that we get what's called partial charges. So a magnet has a charge. It's going to attract its opposite. All right? Same thing with chemical structures. These structures have partial negatives. They're going to attract the positives. The hydrogens have a partial positive charge. They're going to attract anything that's negative. And that means then that our water molecules can stick to themselves. That's why a droplet kind of forms and stays, a circular droplet instead of like spreading out smoothly. And it's also why that droplet is going to stick to a surface. Why it hangs on the edge of a leaf, for example. It's through these positive charges. It also has an effect in that it's going to attract and help to break down things that are in the water or solids that we place inside the water. This is why we call water the universal solvent. So solvents will dissolve things that are like them. Right? Oil and water, they're complete opposites. They're not going to dissolve each other. They mix together, or they separate out. But if we put water in with other molecules that also have some of these partial charges, now we're going to get things that dissolved into our water, which we then utilize for our beer brewing process. All right. For example, we're going to talk about acids and bases. All right. So acids are compounds that will break apart in our water. All right. So this is HCl, is a hydrochloric acid. These are two molecules, two atoms bonded together. In the presence of water, they will produce a chloride ion, so a chloride that has a charge, a negative charge, and it will produce a water molecule that has like an extra hydrogen on it. We're going to call it H3O. Right? We have this extra hydrogen. What this does is going to cause a drop in our pH. All right, it's going to cause a drop in our pH. And that's why we call this an acid. Because if we put this in water, it's going to cause the pH of our water to decrease. It makes it more acidic. Vinegar, that's an acidic compound. Orange juice, that's acidic because it had some acids on it. Bases, oh, that's better. Much better. Bases are a little bit different. All right, so now with the bases, instead of breaking apart, it's going to join up with the water to get a positive ion, and it gets that positive ion by taking one of the hydrogens, and it's going to leave an OH negative or hydroxyl group. All right, so this is ammonia. It's ammonia gas. When we bubble ammonia gas through water, we get this ammonia solution. And the solution exists as having water molecules, we have this ammonium ion, and we have this hydroxide ion. What this will do is cause an increase in pH. That will cause an increase in pH. Now, under normal situations, under equilibrium solutions, water dissociates by itself. So in our natural solution, we have our H2O that actually exists as this H3O positive and the OH negative. That's what naturally occurs in our water supply. If we are balanced, completely balanced, then these are balanced. And that gives us a pH of 7. So our pH 7 is a neutral pH type solution. What happens, though, if we get out of balance? What happens if we put something into our water and we get more of these H3Os? Well, if we have more of these H3Os, our water always wants to be imbalanced. So what's going to happen is if we have more of these, right, our water is going to try to shift to kind of get things back to normal. And when that happens, then our pH is going to change. If we have more OHs in our water, that's going to cause our balance to get disrupted. It wants to go back into a balanced system, and it's going to cause our pH to change again. All right? We're going to utilize, and we have to pay attention to these changes in the pH because pH affects a lot of things in our mashes. All right? So what happens in our mash? pH in the mash. What happens in our mash? What does the mash accomplish? Anybody? What do we convert into something else?
Sugars and starches.
Reverse. Yeah, we take our starches from the seed, right, and we're going to convert them into sugars. What does that? It's our enzymes, all right? So if we look at a graph of enzyme activity, as a function of our pH, what we see is that our enzyme activity is going to go up and then it's going to go down. So there's a range of pHs in which our enzymes are actually active. All right, so this is, if we do amylases as an example. So alpha and beta amylase, those are the two compounds that take our starches and convert them to the sugars. What we are looking at is a fairly narrow range of pHs where we get our optimum activity. And that's between 5.2 and 5.8. If we're outside of this range, then our enzymes aren't going to really be effective, really won't be working very effectively. All right, so if we're here, all right, that line could give an expected gravity of, let's say, 1.05. So Expected gravity, this is specific gravity. This is a measure of how much sugars are in our solution. All right? The higher the number, the more sugars that we have. As this number goes up, all right, we not only have more sugars, but now we're going to expect higher alcohol content in our finished beer because we're giving the yeast more food. All right? So we may have an expected gravity of 1.5, but let's say we are right over here. Right, we're right at the edge where we're not at the peak. We still have some activity, but we're not right where we wanted. We may only get 1030 at that point. All right, so our brewers, big brewers, home brewers, worry about what we put into our water, what we put into our mash, because we're always striving to get the maximum amount of sugars out of our grain. And we target this pH range, try to be right in our sweet spot that maximizes our enzyme efficiency. So what's going to affect the overall pH? Well, it's our water. Water has buffering capability. And the most common molecules that buffer this is the carbonate system. All right, so carbon dioxide as a gas can be dissolved in water. Right? You've seen it. I think soda streams, right? You've heard of soda streams. You take water, you carbonate it. Right? So what we're doing is getting carbon dioxide dissolved in water. What that's going to produce is carbonic acid. Right? H2CO3. But that's not how it exists actually in the water. This actually exists in balance with, so it goes with other water molecules, hydrogen bicarbonate. Oops. So carbonic acid combines with other molecules to get HCO3 negative plus H3O positive. And then with another molecule, water molecule, we will get our H3O positive and CO3 2 negative. So everything's going to exist in balance. So we bubble in our CO2. What ultimately happens? We produce a lot of this. And this makes it unbalanced. So we're going to have all of these shifts happening, ultimately producing more of these. These contribute to a lower pH. So carbonated beverages tend to have lower pHs than non-carbonated beverages. All right, what about some other things? Well, if we add malts, what happens to our malts? Well, our malts might combine with some of these. So some compounds in our malts may be a positive compound. It may bind with this, all right? And if this goes out, then how do we respond? Well, we're going to respond by breaking down more of this or by combining more of this to kind of get things back into balance. All right? This buffering system, this carbonate system exists out in nature, in our ponds, in our streams, in the ocean. All right? This is the most common buffering system that we have out there, and it's one that we have to be aware of. So if we have a high pH of a solution, and what's going to happen is that we're moving that way to lower the pH. If we have a low pH solution, everything's going to be pushing this way to try to reduce our pH. All right? How do we measure this overall? We measure it using something called residual alkalinity. So residual alkalinity measures this buffering capability. So it's going to depend on what all is in our water. How much calcium we have, how much magnesium we have. In distilled water, we have 0. It is just pure water like this. In reverse osmosis water, we're close to this, not quite 100%. The membranes themselves have an efficiency anywhere from about 90 to 95%. Kind of depends on several other things, but we're close to this. All right, so this residual alkalinity takes into account everything that's in the water, and tells us how well our water will do at resisting changes to pH. All right, so higher alkalinities we have increased resistance to change. Lower values, we're going to see changes pretty quickly. Where does this all fit in? This all fits in with our grain. So we talked about grain. We talked about how it was made. We talked about the specialty types. We talked about the kilning process to produce, roasted and toasted types of malts. I think that's where we're at. All right. So, as an example, the effective grain. Most common base malts in a beer will be a 2-row malt or a pale ale malt. These are probably the two most common grains. They are very light in color. Right? These two grains have a very small effect on our pH. So if we use them, yeah, we're going to see a slight decrease, but not a whole lot. As we increase and look at toasted grains, we have what I'll call an average effect on our pH. We get an effect that's more than our pale ale malts, but less than our last one, which has a large effect. All right. And what marks these? Color of the grain. So the pale and the 2-row are very light colored grain. They haven't been toasted or roasted very long. Their kilning process was short. It was at lower temperatures. Our roasted grains, dark in color. They've been roasted at higher temperatures, in a drum roaster probably, and so forth. These all have an effect. All right. So our lighter grains have a small effect on pH. The light grains have a small effect. Our dark grains have a large effect. So why do we worry about this? Well, we worry about it because of the water supply that we're using. If our water supply has a high residual alkalinity, then if we use any of these grains, we're not really going to be able to affect the pH much. And if this water was at a high pH to begin with, we're trying to get down here. Those grains aren't going to be sufficient. So we're going to have to do something to bring that pH down. That something could be to say, hey, let's use roasted grains instead. Let's increase the darkness because these roasted grains will bring our pH down to this range so that we get our expected gravity. We get our high efficiency. All right? So how do we know which ones to use? In general, we classify our water based on its hardness. And the hardness and the residual alkalinity are related. Right? So generally, hard water has a high residual alkalinity. Soft water has a low residual alkalinity. Difference in these is based on how many ions they have in their water, what their buffering capability is. All right? So soft water has low buffering capability. Hard water has a high buffering capability. What does that mean? Low buffering capability, if we use roasted grains, we can decrease our pH too much. And thus, we hurt our efficiency. If we use roasted grain in a really soft water, we're going to be at the really low end, right? If we use only pale ale malts in this high cut buffering capability, we won't get down far enough. We're going to be at our upper end. So we have to look at our water supply. We have to look at residual alkalinity and then base our profile, base our beers on that water. We're going to talk about this a little bit more specifically next week. Next week, Monday. All right. On Monday, we're going to talk about the beers of the United Kingdom. All right. Beers of the United Kingdom, porters and stouts originated there. Porters originated in London. All right. IPAs originated in northern England. All right. Ireland is known for their stouts. Question is why? Why did they originate there? Why did they why were they successful? It's our water. That's why. That's why. All right. So if we can't use our grains to adjust our pHs, is there something else that we can do? There is. So the most common water addition that we can use. So if we have, like here, we have very hard water. Our pH is up in the 8s. All right. We got very, very hard water. It's really not good for brewing. And in general, if the water doesn't taste good to drink, it's not going to make a very good beer in general. All right. If you don't believe me, take tap water here, make some coffee, all right, make some tea. You can taste it. You know, yes. I'm not from Texas. It was a pretty big shock when I came here. And on my interviews, I got picked up from. We'll take a break. I got picked up from the airport, and we went right to lunch. There's a place, Pack Saddle, right on Knickerbocker, a barbecue place, and department chair, the old department chair is there, and we ordered drinks, and I said, yeah, I'll have, I'll just do the water, I'll just do like iced tea or something like that. And they brought it out, and he got like a Coke or something like that. I took a sip, and he go, He's like, oh yeah, I forgot to tell you, don't drink the water. Yeah, thanks, great, awesome. All right, anyways, water additions. What can we do to fix our pH? All right, so if we can't use our grains to fix it, is there something else? Yeah, there is. All right, so if we have very hard water like we do here, and we want to produce a very pale or light colored beer, we have to do something to get our pH down into this range. That's something. The most common addition is going to be lactic acid. All right. Second most is probably phosphoric acid. So phosphoric acid is a food grade acid. You'll be surprised to see how much is included in it. We could use citric acid, but these two are favored because they really don't contribute any sort of taste. Citric acid can also be used. Some people claim they can taste it. I can't really tell you. All right, I've never used it. All right, phosphoric acid, definitely food grade acid. It's a neutral flavor. We don't really use phosphoric acid at the homebrew scale because it's a lot harder to work with. It's a lot harder to work with, a little bit more dangerous, not as easy to purchase. All right. Lactic acid, though, we can utilize. We can purchase it. All right. I've used it. All right. This is naturally occurring as well. So naturally occurring, you might ask? Yeah, we have bacteria that will naturally produce this. So one way we can fix our pH is to add the liquid itself. Right? We add the pH at mash to bring the pH down. Another way is to mix our grain in the water and let it sit out. So heat it up a little bit and then let it sit out to sour. The souring bacteria will produce lactic acid. That lactic acid then gets us back down into our range. So when we do our conversion, our sugar conversion, right, it's going to work. Downside of this, lactic acid kind of gives a tartness to it, which some people like, and I think different styles have worked. So historically, what the brewers did was mix the grain with the water and then let it sit overnight. It allowed the bacteria to naturally produce this lactic acid, which fixed their efficiency problems. Modern day fixes, just to use the chemicals. All right? You don't have all day. Any questions on pHs? So pH affects the mash, and we're always going to be careful with our pHs. The other aspect of water is how it affects the final product. Or perhaps more specifically, how it affects our perception of the final product, all right? So water will affect our perception. Water affects our perception of beer. The question is how? Who likes watermelon? Who's had watermelon? Probably everyone, right? Who puts salt on their watermelon? Why do you do that?
Just like the taste of it.
You like the taste of it. Who else has used salt? I think I got a better answer than that too. You like the taste of it, yeah. Why?
Contrast.
What's that?
Contrast.
Maybe. Does something else too. All right? Does something else, and this is what we're interested in. We're interested in chloride to sulfate ratios. We are interested in how much of this Cl negative, this chloride ion we have in relation to sulfates. In relation to sulfates. How does this affect our perceptions? Chlorides accentuates sweetness. Why did you like salt on watermelons? It accentuates the natural sugars in that watermelon. Right? You like it, you perceive it as liking it, and you probably detect some of the salt that's in there. Yeah, I really think it improves the flavor. Chemically, when our brains get that sugar, endorphins go off. Say, oh, we like this. You crave it. Our body craves more of it. Right? Any organism that gets that sugar, our body craves more of it. If we have more chlorides in this beer, it's going to accentuate the sweetness aspect of the beer. What does the sulfates do? This is going to accentuate the bitterness of our beer. And this is the bitterness caused by the hops. All right? So, if we are heavy towards the chlorides, we accentuate the maltiness aspect of it. If we shift more towards the sulfates, we're going to accentuate the bitterness parts of it. Our example to demonstrate this, can't taste it, you have to take my word for it, are the Pilsners. We've got two Pilsners. We have the original, which is the Czech Pilsners. And then we have the copycats, which are the German Pilsners. And I say copycats because they basically are. All right? Czech Republic was world renowned for their Pilsners. What is a Pilsner? It's a lager. It's a lager beer. It is basically entirely made with a type of two-row malt, a Pilsner type of malt, very low in contribution to pHs. Right? Did they add anything to their mash? No. All right. So in order to get this pH, our Czech Pils have naturally soft water. And not just like regular soft water. It is really, really clean and almost pure water. So when you only use these Pilsner malts, it naturally gets down to the pH that it needs to get, which means our efficiencies are going to be great. right? Our efficiencies are going to be great. They made these, and the pills kind of developed because until this time, you didn't really brew these lighter colored beers. They were brewing the darker colored beers because of the efficiency problem. Glass also wasn't very big. So it wasn't until glass came around where people said, oh, I want to look at these lighter colored beers, these clear beers. And once people started saying, oh, I like these, then they started copycatting it. The Germans, on the other hand, had difficulty. They had difficulty producing the beers. Now, they understood the pH. They could fix the pH issue and approach the efficiency. But they couldn't get the taste. And it's because of our chloride to sulfate ratios. So this is naturally soft water. Our chloride ions in this Czech pills were more than our sulfates. And that accentuates the malt character of this style. It's maltier than our German pills. The German pills suffered from sulfate ratios that were too high. And they couldn't replicate this classic Czech Pilsner. So these beers ended up becoming more bitter. Question? So, one other component to this that I don't know if we mentioned it. So IBUs, International Bittering Units, gives us a measure of bitterness. It's a measure of bitterness. All right? The higher the IBU, the more bitter it is. IPAs are advertised for having high IBUs in their beer because they strive to be bitter. All right? Our Czech pills, as you perceive it as being maltier, yet you have higher IBUs. Our German pills, we perceive them as being bitter, but we have lower IBUs. What produces this perception? It's our ratios. So you can manipulate these ratios. You can take a beer, exact same recipe, brew it 2 times. One time we have, let's say, twice the amount of chloride ions compared to sulfate, and we're going to perceive our beer as being maltier than a beer that's produced with, let's say, twice as many sulfate ions. Kind of another piece of the puzzle that we have to be aware of. All right? Questions? This is one reason why certain styles, certain places became known for their pale ales or their IPAs, their India pale ales, because they had this ratio that really accentuated a bitterness or more a clean bitterness. Not a harsh bitterness. All right, we're done here. On Monday, we will pick up. We'll talk about different styles and origination of the styles and focus on the water. All right, and then on Wednesday, we will finish up with glassware. All right. That final piece, that presentation part. All right, don't forget that summary.